Integration and differentiation are powerful tools of math. They can show us how fast an object is moving based on its position versus time graph, and how fast and where it is based on its velocity versus time graph. However, these operations have limitations. For example, there are many cases where integral problems don't have clear defined answers that are easy to work with. These integrals need their own special antiderivative functions that fall under the category of non-elementary functions. There is an uncountably infinite number of them, and any random squiggle on a graph, such as real-world data, has an uncountably tiny probability of being an elementary function. And that is what Taylor polynomials are for. We can use Taylor polynomials to describe these functions. They are very good approximations of different functions, and they have the added bonus of being polynomials, so they work really smoothly with integration. To show a real-world example of a Taylor polynomial in use, I will use my phone sensor to come up with velocity data. Then I will find the Taylor polynomial of that velocity data, and finally I will integrate and find the position versus time function of that data. Okay, I wasn't able to find a speedometer anywhere on my phone, but I do have an accelerometer. So I'm gonna record the acceleration and convert it to velocity. Here's the acceleration graph that I got. I drew a line on it to make it within my human capabilities to find a Taylor series for it. But if you add enough terms, you could do the whole squiggly line. But that's a little out of my scope. After looking at the graph, I've noticed that at 5 seconds, the graph was accelerating at about 0, so I'm going to center the Taylor polynomial around 5. After noticing that at t equals 4, the acceleration is -1/2, I have found out that the first derivative at 5 is equal to 1/2. To make the process of finding the higher order derivatives easier, I labeled a bunch of points in Desmos that I want the graph to hit, and then I will add a bunch of sliders to a generic Taylor polynomial, and I'll mess around with them until the line hits all of them. After realizing how difficult it is to come up with a Taylor polynomial by hand, I plugged in the data into Google Excel, and then I used a regression line, a 6-degree polynomial regression line, and I have the Taylor series. Now I'm going to integrate it. Although finding the Taylor polynomial for the function was pretty difficult, doing the power rule on all of them to integrate it was pretty easy, which is the whole reason why I'm doing the Taylor series. This right here is the antiderivative of the Taylor polynomial, aka the velocity graph. Here is what the acceleration and the velocity Taylor polynomials look like together. And that concludes my video on using Taylor polynomials on real-world data.